Welcome all. Now we are going to discuss the Corollary 6.3. It has two statements, and the first one is let x and y be normed spaces, f from x to y be a linear map, then f is a homeomorphism if and only if there are constants alpha and beta positive such that beta into norm x less than or equal to norm f of x less than or equal to alpha into norm x for every x element of x. In case there is a linear homomorphism from x on to y, x is complete if and only if y is complete. And the second statement is let x and y be normed spaces with x finite dimensional, then every bijective linear map from x to y is a homeomorphism. And all norms on capital X are equivalent and x is complete in each. If dimension of x is finite, if dimension of x is equal to n, then there is a linear homeomorphism from Kn on to x. Okay, let's look at the proof. For the first part, we have x and y are normal spaces and f from x to y is a linear map, and we are supposing the one side, that is f is a homeomorphism. Okay, we have to prove that there exists constants alpha and beta positive satisfying that condition. We have f is a homeomorphism, means f and f inverse are continuous maps. Okay, then by 6.2, theorem 6.2, we can see that there exists constants alpha and gamma greater than 0 such that norm f of x less than or equal to alpha into norm x for every x element of x since f is continuous, and norm f inverse of y is less than or equal to gamma into norm y for every y element of the range of f since f inverse is continuous. Okay, now choose x element of x with f of x equal to small y. Then we can write f inverse of small y is equal to x, right? This we apply in equation 1. We get norm of capital F of x is less than or equal to alpha into norm x, and norm of f inverse of y less than or equal to gamma into norm y. When we substitute f inverse of y is equal to small x and y equal to capital F of x, we will get norm of f of x is less than or equal to alpha into norm x, and norm x is less than or equal to gamma into norm f of x, right? Then we are just combining these two. We get norm x by gamma less than or equal to norm f of x less than or equal to alpha into norm x. Okay, taking beta is equal to 1 by gamma, we can write it as beta into norm x less than or equal to norm f of x less than or equal to alpha into norm x. Okay, so we have found that constants alpha and beta positive satisfying the required condition for every x element of x. So the necessary part is proved, and conversely we have to show by supposing that f is a linear map satisfying this condition, we have to show that f is a homeomorphism. So conversely, suppose that f from x to y be a linear map and beta into norm x less than or equal to norm f of x less than or equal to alpha into norm x for some alpha and beta positive, and for all x element of x, let it be equation number 2. And from this inequality, norm f of x less than or equal to alpha into norm x, this implies f is continuous by the theorem again 6.2. Okay, now let f of x1 equal to f of x2 for some points x1 and x2. This means that f of x1 minus f of x2 is equal to 0, and since f is linear, we can write it as f of x1 minus x2 equal to 0. Okay, also by equation 2, also from equation 2, by substituting x1 minus x2 in the place of x, we can see that beta into norm x1 minus x2 is less than or equal to norm f of x1 minus x2, and that is 0 actually. So beta into norm x1 minus x2 is less than or equal to 0. but norm is always greater than or equal to 0 and beta is greater than 0. This means that this beta into norm x1 minus x2 is equal to 0. and beta is greater than 0. This means that we get norm of x1 minus x2 equal to 0, that is x1 is equal to x2. Thus we have found that f of x1 equal to f of x2 implies x1 equal to x2, means that the function f is injective. Okay, also we have f is continuous. Thus the function f is injective and continuous. So since the function is injective, that is since the function is 1 1, the function has an inverse. That means f inverse exists and is clearly linear also by theorem 2.4a part, that is f inverse from range of f to capital X exists and is clearly linear also. Now we have remained to show that f inverse is continuous. Okay. Also from equation 2 we have beta into norm x is less than or equal to norm f of x. So substitute f of x equal to small y and x equal to f inverse of small y. We can say that beta into norm f inverse of y is less than or equal to norm y. So we get norm of f inverse of y is less than or equal to 1 by beta into norm y. This is true for every y element of the range of f, and taking 1 by beta as a constant, we can say that by theorem 6.2 that f inverse is also continuous. So we have the function f from x to y is linear and f is continuous and f inverse is also continuous. So the function f from x to y is a homeomorphism. That is the first part. And one more thing in the first part is in case there is a linear homeomorphism, then x is complete if and only if y is complete. So we have to look into that. Suppose there is a linear homeomorphism f from x to y and assume x is complete, we have to show that y is complete also. Okay, so we are taking a Cauchy sequence f of xn from the space y, and again, since f is a homeomorphism, we have f and f inverse are continuous, and so we can write beta into norm xn minus xm is less than or equal to norm f of xn minus xm for some beta greater than 0. Because of the first part we have proven, since f is a homeomorphism, we can write that condition. Okay, this means that beta into norm xn minus xm is less than or equal to norm f of xn minus f of xm, and we have f of xn, the sequence f of xn is a Cauchy sequence, and this means that sequence xn is a Cauchy sequence in x, and since x is complete, this sequence xn converges to some point x in x. Okay, and so since capital F is continuous, we get capital F of xn converges to capital F of x in y. This means that the Cauchy sequence that we have considered is convergent in y. This means that the space y is complete. Now conversely, suppose capital Y be a complete space, and we have to show that capital X is complete. So take a Cauchy sequence xn from x, and since f is a homeomorphism, by the first part we can write norm of f of xn minus xm is less than or equal to alpha into norm xn minus xm for some alpha positive, and this means that norm of f of xn minus f of xm is less than or equal to alpha into norm xn minus xm. And since xn is a Cauchy sequence, from this we can infer that sequence f of xn is a Cauchy sequence in y, and since the space y is complete, we can say that the sequence f of xn converges to some point y in capital Y. And so since f inverse is continuous, we can write f inverse of f of xn converges to f inverse of y in x. This means that sequence xn converges to f inverse of y in capital X, and so the space capital X is complete. Okay, this is the first part of the theorem. Now for the second part, we have x and y are normal spaces with x is finite dimensional, and let f from x to y be a bijective linear map. We have to show that it is a homeomorphism. Okay, since x is finite dimensional, we know from theorem 6.1 that f is continuous. Okay, and f is bijective, we know the f inverse exists and also f from x to y is continuous, and f is bijective, and capital X is capital X is finite dimensional, means that capital Y is also finite dimensional because f is bijective, and f inverse from capital Y to x become continuous since y is finite dimensional, and linear also. This means that the function f from x to y is a homomorphism. That is, every bijective linear map from capital X to y where x is finite dimensional is a homomorphism. Okay. Now we have to show that any norms on capital X are equivalent. So we are taking two norms, norm and norm dash in capital X. We have to show that they are equivalent. Okay. Now we are considering the identity map capital I from x to x defined by I of x is equal to x for every x element of x. This map is clearly linear and bijective. Okay. And since we have dimension of x is finite, and capital I and we know that capital I is clearly bijective and linear. So by the above part we can say that this capital I is a homomorphism. So by theorem is a homomorphism. So by the first part of this theorem we can say that there exists constants alpha and beta positive such that beta into norm x is less than or equal to norm dash of I of x less than or equal to alpha into norm x for every x element of x. Because we are considering two norms in the same space, so on capital X we are taking as a domain x with norm and the codomain x with the norm dash. Okay, so I from x to x means I from x with the norm to x with the norm dash. So norm of I of x means it is norm dash of I of x. Okay, so this means that beta into norm x is less than or equal to what is I of x, that is x. So beta into norm x is less than or equal to norm dash of x less than or equal to alpha into norm x for every x element of x. This means that the two norms norm and norm dash are equivalent by the theorem 5.7. Okay, thus every norms on capital X are equivalent. Also, since the dimension of x is finite, x is complete in each norm because suppose dimension of x is equal to n, then we can find a basis y1, y2, etc. yn for the space x and define capital F from kn to x by f of tuple k1, k2, etc. kn is equal to k1 y1 plus k2 y2 plus etc. plus kn yn, the linear combination of the basis elements. Okay, then clearly k1 y1 plus k2 y2 plus etc. plus kn yn is an element of capital X, and clearly f is bijective and linear. Just try to prove it. Okay, so we have defined a bijective linear map on the finite dimensional space Kn. This means that by the above part capital F is a homomorphism. Okay, so capital F is a homomorphism and we know Kn, the space Kn is complete. This means that the other side capital X is also complete in every norm. That's the proof. Thank you.